Hey guys, what's up? This is AJ again of Bridging Code, and for this episode, we're going to be talking about event-driven architectures, how it works, and how we can go about implementing it using the widely used open-source event streaming platform Apache Kafka and Java with the use of Spring Boot and its dependencies to support Kafka. So, when we hear about event-driven architectures, what exactly is an event? An event is a change in state. It can be anything from your credit card bill payment for this month. Once you paid, the state or the status of your bill is changed from unpaid to paid. Or when taking an online exam, the status is changed from not taken to completed. Or in e-commerce sites, when adding an item to your shopping cart, the new item added counts as an event, and the e-commerce app will react to it, and the number of items in your cart will increment, and also the value of that item will be added to your total amount. Now, an event-driven architecture is an architectural paradigm that uses events to trigger and communicate between loosely coupled applications or services. These events will need to be published to an event broker platform and be sent over to consuming applications. An event may contain a state at a certain point in time, as denoted by the mail with a clock symbol in this diagram, like the status of a transaction, the amount paid, the items in your shopping cart, the shipping status, and so on. Or notifications like your order has been shipped, or you completed the course, or a certain amount has been credited to your account. Normally, an event-driven architecture is comprised of three components. The producers are apps or services that publish events to an event broker platform. The event router or broker, which is a platform or middleware that takes in events and routes them to their respective consuming applications. And of course, the consumer, which is another app or service that consumes to a particular topic in an event router, receives the event or stream of events and does something with it, like save the state to a persistent storage or for analytics. Keep in mind that producers and consumers are decoupled, meaning they are not aware of each other. So the good thing about this is you can modify, deploy, and scale them independently as necessary. When designing an event-driven architecture, there's usually two models that you could implement, both of which we will be doing later on when we start to code our app. The first one is a pub-sub model, or publish-subscribe, which is when the event or messaging platform, for our case that will be Apache Kafka, keeps track of subscriptions. When an event is published, it sends an event to one or more consumers. After an event is received, it cannot be replayed, or you can no longer refer to it again at a later time, and new subscribers do not see that event. The other one is the event stream model, where events are written as a log and is strictly ordered within a partition. Consuming applications aren't necessarily subscribed to receive individual events. Rather, they receive a stream or an unbounded flow of events, and they can read from any part of that event. Just some of the benefits of event-driven architectures are it is asynchronous. Event-driven architectures asynchronously receive and process events without getting blocked by earlier events that have transpired. It is scalable and independent failure, since your producer and consumer services, as I've mentioned earlier, are loosely coupled. They fail independently. And the event router should be elastic enough to be able to scale as needed and accommodate surges in workload, like what Apache Kafka is, which we'll be talking about later. It is also good for auditing and point-in-time recovery. You have this sequence of events that have transpired, and the event router or broker acts as a centralized location to audit your application. You can kind of think of it as a ledger, which is an immutable order of events. Since these events contain snapshots of a state, you could even use this to recover objects in their previous state or any state at a certain point of time by rewinding events from the past. Now, Event-driven architectures aren't perfect, it also has some flaws. Definitely, it is not one of the easiest architectures to implement. There is an added routing middleware which could add to the complexity of the architecture of your system, and it is also prone to over-engineering. For most cases, it is non-ACID compliant. Due to the asynchronous distributed nature of event-driven architectures, you are going to have difficulties in maintaining transactional support. Handling of duplicate transactions could present to be a challenge since processing of multiple events could happen at the same time. So if you have a use case for heavy atomic transactions, then you might have to think twice about implementing this design pattern. Now, I'm not saying that you couldn't do transactional operations with it. It is still doable. Some event streaming platforms started to support transactions anyway, and I think it's not also long ago that Kafka did the same. It's just that it's far from being the best pattern for ACID compliance. Nonetheless, if there's a requirement to implement transactions over this kind of architecture, what you could do is to think about grouping the events that are dependent on each other and choreograph the coordination between the services that process these events, which is what you would normally call a saga pattern. And of course, the cost. It's either you maintain a reliable and fault-tolerant servers on premises where you could run Apache Kafka, or pay a usually expensive subscription to a provider like Confluent to have it on the cloud. But if you have the budget allocated for this, this won't be an issue. The event router that we will be using to implement a very simple event-driven architecture is the Apache Kafka. Apache Kafka is an open source distributed event streaming platform used by more than 1,000 companies out there for high performance data pipelines, streaming analytics, data integration, and mission critical applications. It was originally developed by a team of engineers from LinkedIn, but was later open sourced in 2011 with Apache. So with using Apache Kafka, you could be having multiple applications or services that write events to a Kafka cluster, while at the same time, you could also have multiple consumer apps that subscribe or stream events from Kafka. A Kafka cluster is a collection of brokers. You can think of these brokers as like servers in a data center, and they are networked together and function together as a single cluster. Brokers could be actual physical servers, or a single rack, or VMs, or whatsoever. In most cases, you're not going to be concerned about them too much, especially if you're using Kafka on the cloud or as a platform as a service like Confluent or Kafka and Heroku. Most of the configurations are abstracted away from you so that your only concern is making your apps work with Kafka. The point is, unless you're someone like a system or DevOps engineer directly involved in managing Kafka clusters for your company, you usually don't need to be concerned about the thorough inner workings of Kafka. If you are, feel free to check out some of the videos I've linked in the description below that discuss deeply about how Kafka works, as presented by Tim Berglund of Confluent. Now, also in the diagram, you can see a lone rectangle below connected to the Kafka cluster. That is Zookeeper. Zookeeper is the one in charge of cluster management, and also in failure management, it decides which among the replicated brokers can be the new leader when a broker fails. And yes, brokers are replicated for redundancy, which makes Kafka a more fault-tolerant platform. ACLs or access control lists are also stored in Zookeeper. Now, a broker can store multiple topics where producers write events on. A topic is a collection of related events or messages. When a producer app produces an event, you will need to specify the topic where you want to write or publish it to. The number of topics that can be created in Kafka is theoretically unlimited. A partition breaks up a topic into logical pieces, and those topics are allocated into different brokers. So you might think, oh, a broker is composed of topics, and topics are made up of partitions. So the case is that these partitions belong to a single broker. Well, that is not the case with Kafka. And the idea behind this is that topics can scale forever in an individual broker, which could be an actual server or a VM or whatever physical resource you might think of it. So a broker is actually managing multiple partitions from different topics. Instead of forcing these brokers to scale up as the topic size increases, we scale out by distributing the partitions of a topic into multiple brokers, and this significantly improves the I/O and parallelization performance of the cluster. This is what makes Apache Kafka highly scalable. Now, not only is Apache Kafka good at scaling out, it is also known to be very fault tolerant because the partitions are also replicated into different brokers. The replication factor, which you could configure in your application, is the configurable number of replicas of a partition. For example, in our diagram down here, it has a replication factor of 3. So imagine when a broker goes down, which houses a certain partition, the events aren't instantly lost because you have a backup of that partition in another broker. Among the replicas of a partition, there is always a leader partition where producers and consumers write and read events respectively. And when this leader partition goes down unexpectedly, any of the follower partitions can be promoted as the new leader, which is decided by Kafka using Zookeeper. So what we will build now is a very simple e-commerce themed system. And as mentioned earlier, we will try to implement the two models we talked about, which are PubSub and event streaming. So we start off with the front end or the e-commerce website where a customer would order products. Now, we aren't actually going to build a front end UI of the shop, but we will just open up a RESTful endpoint to submit a JSON request of the product order to the producer app. The producer app will then treat that request as a product order event and write this event to the product orders topic, which we will create later in Apache Kafka. Now, our implementation will have 3 consumers. One of them will subscribe to product orders topic to take in individual events and do some kind of process with it. Imaginably, it may save the state in that event in a persistent storage or line it up to logistics for shipping, but for our case, we're not going to be doing any of that. Maybe we'll just print out the event we received to keep things simple, just to demonstrate PubSub. 2 of our consumers will be streaming the topics in the Kafka cluster, one of which will be streaming events from product orders. Maybe we'll just filter out something from the event stream, like if the current quantity is 0, and direct the stream to another topic called product orders analytics. The last consumer will stream from the product orders analytics topic and just do a tiny bit of analytics, like counting the number of orders per category and then saving it to a materialized view, which you will learn about later, so it can be queried at a later time. And then finally, send over the results to a front-end view in a JSON format to demonstrate the concept behind how dashboards work. Now, keep in mind that this diagram will not be an accurate representation of what we will actually implement, but rather just briefly describes it. Realistically, the producers and consumers are literally decoupled and deployed in their own environments or containers, but for demonstration purposes, they will still be decoupled, but they will all be running under a single Spring Boot app project. So now we have to think about how we're going to make use of Apache Kafka. Well, you have a few options here. You could install Apache Kafka into your local machine. I have pasted a link to the instructions on how you can do this in the description below. You could also have everything in a Docker container. So you'd have this Docker image where your Spring Boot app will be running there, and also your Apache Kafka is in there. Or the easiest for me, and what we're going to do in this tutorial, is to just run it on a cloud. There are several PaaS providers out there that offer fully managed Apache Kafka on the go. There is Kafka on Heroku, and we also have Confluent Cloud. I'm going to use Confluent Cloud because I've already got an account here, so might as well just use it. Now you know you have multiple options to run Apache Kafka. Feel free to choose what you think is best for you, but I'm going to go for the fully managed option just so I don't have to set anything up. If you decide to go for Confluent Cloud, you'll need to create a cluster, like what I already have here. It's going to ask you which cloud provider you want your cluster to be set up on. You can choose from AWS, Google Cloud, or Microsoft's Azure. I've chosen Google Cloud for this cluster because it appears to be the cheapest option, because you will also be asked to provide your credit card info when creating a cluster. But don't worry, Confluent Cloud gives a $200 credit, which serves as their free tier, and you're not going to be charged anything until you exceed this credit limit. Here at Confluent, before you create a topic, you should create an API access first, which is the credentials that we will put in the properties file of our Spring Boot app later. I'm not going to create another one because I already have one here. To create a topic, we can go to Topics and click Create Topic. We're going to be creating two topics. The first one is product orders, where product order events will be written to. The default number of partitions is 6. We'll pretty much just create this topic with the default configs, but if you wish to tweak some settings, you can go to Customize Settings. You will see a few configurable settings here. We have the cleanup policy, which is basically just a retention policy of your log segments. There is the retention time, which sets how long you can store the messages or events in Kafka. And yes, Apache Kafka also has quite a bit of persistence built in, but I wouldn't rely on it. If you need to save something important from the event, it's best that you save it in an actual persistence storage like a relational database. We also have the retention size, which is just the maximum size a partition can grow before it is discarded by Kafka to free up some space. And then finally, we have the maximum message size, or the max size of the message you can write in a topic. So by default, it is about 2 megabytes. I'm not sure if you can go larger than this. I think not. So let's just create this topic. And we have to create another one, which is product orders analytics, still default configs. I have already set up our Spring Boot app project and prepared the classes and interfaces and the properties YAML file just so we don't have to worry about these later. So I'll first show the Maven dependencies that we'll use for this project. First off, you need to ensure that you have these two dependencies from Spring Cloud, the Spring Cloud Stream Binder Kafka and Spring Cloud Stream Binder Kafka Streams, which is Spring's official binding support to work with the Kafka Streams library. We also have the actuator dependency of Spring Boot for health checks, but we're not going to make use of this. We also have the Spring Boot Starter Web to open up an HTTP endpoint to display our analytics dashboard. And then there is also the Spring Boot Starter test, but we're not going to write any tests for this demo. This was just included here somehow by default. I think you should also be mindful of the version of Spring Cloud Stream dependencies that we'll be using throughout this project. As of making this tutorial, I think the latest version is Horsham.sr9, which is what I'm using. We also have the product orders event class, which is the model of the event that we will publish and stream. As you can see, it's a fairly simple class. It just contains the number of the name of the product, what category does it belong to, and the number of orders for this product. Now, let's talk a bit about the configurations for this project, which I must admit, it took me quite a bit of time at first to figure out and get my app up and running with Apache Kafka and Confluent Cloud. The config is quite a handful. You can pause this video and copy this right off the bat, but you don't really have to because I have shared the link to the code repository in GitHub where this is all uploaded in the description below, so please refer to that. Now what you need to take note of here are these bindings, which just contains the names of the topics we created earlier. And these will all be referred from the product order bindings interface, so we can publish to, subscribe, and stream from topics in our Kafka cluster. These are just acronyms. They are purely arbitrary, and it's up to you how you're going to name the bindings to your topic. POIN stands for product orders in, which means we'll be receiving an individual event from the product orders topic. PO out is for product orders out, which will be an outbound binding for us to write events to the product orders topic. POS in is the same from PO in, except we want to receive a stream of events instead of just an individual event. PA in and PA out are the same from the others, except these are inbound and outbound bindings for the product orders analytics topic. Let's first work on implementing pub/sub, and the way we do that is we refer to this configured bindings from our product orders binding interface. By the way, we also have the default SERDI here. SERDI just means serialization and deserialization. An event is composed of a key and a value. We want the key to be serialized and deserialized as a string, while we want our value, which is the product orders event, to be serialized and deserialized in JSON. This is just the default SERDI, and this can be overridden in the Java code later. Here is the URL or address to our Kafka cluster, and here are the credentials from the API access in Confluent, which I'm not too concerned about exposing to you guys since I'll be deleting this API access and maybe even the entire cluster once I posted this video. We go to product orders bindings interface, and let's first define some constants. Product orders out. The subscribable channel is how we can subscribe to a particular topic and receive events. And we annotate this with @input and specify the topic we intend to bind with, which is product orders in, which refers to the topic name in our application YAML. The @input annotation simply tells Spring that events will be coming inbound from this topic. The message channel is how we can publish events to the topic. And the output annotation simply tells Spring Cloud Stream that events will be coming out of this application. Now, you might be thinking how we can go about testing this app. If you can still recall from our diagram earlier that we'll open up a RESTful endpoint to submit a product orders event, I actually changed my mind about doing that. Instead, let's just have those events be created and published automatically by writing an application runner. So let's first open up the Spring Boot app class and enable bindings. Specify product orders bindings to get everything to work. Now, I'm just going to quickly write that application runner with a runnable code inside that publishes events every second, just so we don't have to worry about it later. Um, or bindings out, run hash map here, spring orders hash map, books, uh, Romeo and Juliet, Romeo and Juliet, Sherlock Holmes, put toy, string, Hot Wheels, food, chicken burger, steak, pizza, videos, Avengers, crazy love, music, hearing, next int order size, should be array brackets. Category. Was event, builder, payload event. Now, let's head over to Product Wars Processor class, and this is where I intend to write the code for all our consumers. Let's create a logger. And let's write our subscriber here. We're not going to do anything here but to just log the event we received. Get name, get category, get quantity. Let's annotate this with @stream_listener and specify the topic where we'll be subscribing to, which is Product Wars, and that is binded into this constant. So let's try to run this code. Um, mvn clean spring boot run. This may take some time to connect and integrate with Kafka on Confluent Cloud. Visualizing. And as you can see, we are able to publish messages to the product ORS topic, while at the same time subscribe to that topic and log the events we received. And also from Confluent Cloud, um, oops, we can also see the messages or events being written to product orders. Here they are. Now that we're able to write and receive individual events to the topic, let's start to code the consumers who will be streaming from the topics we created. But first, we need to add the inbound streams binding for product orders topic and the inbound and outbound streams binding for product orders analytics topic, all of which will be referred to the entries in our application YAML file from earlier. Orders, order count. So a case stream is just an abstraction or representation of the actual stream of events that will be coming in and out of your application. It's part of the Kafka Streams library, and you'll see later that we can do a few things with it. Now, let's code the method to stream from product orders topic. Um, let's just filter out orders with a quantity greater than 0. We will stream from product orders by referring to its inbound binding. And then we will send the stream out to the product orders analytics by referring to its outbound binding. Next is we will code another consumer to stream from the product orders analytics. Process analytics. Now we're going to remap the events in the stream and group them by category. Since we remap the events to group them by category, we'll also need to align our SERD into the corresponding types. Our default SERD for the value is a JSON SERD because our value is a product orders event object. That will not be the case here anymore, because the value will now be the number of events per category. Now, when you apply the count method, this should return a K-table, which is then stored in a state store. A K-table is just an abstraction of a table of events, like what K-streams is to a stream of events. A table differs from a stream in that it only represents the state of events at a certain point in time. Usually it's a current time or the latest state. In our case, we want to get the current count of product orders per category at this current point in time. Now, we need to refer to this K table later, which is stored in the state store, to query it, so we need to materialize it with a store name. From a K table, we're going to need to turn it back to a stream because we want to print it to the console just to see the actual current count. We have also annotated this method with a stream listener to stream events from the product orders analytics topic. Now let's go to the controller. Request mapping, shops, AutoWire interactive query service, a query from that materialized view. And now we actually write the API to give us a total count of orders and give us percentage of orders per category. Map string link hash map. Let's refer from the materialized view, which contains the K table. Iterator. Next. Total value. Put total orders. Let's have another iteration here to put the percentages in the map. Vote value. Response entity result. Okay. And now we run this code. Okay. It appears that we're able to stream from the product orders analytics table and log the count of the orders per category. If we try to access the API for analytics, as you can see, it gives us a total number of orders and the percentage of orders per category. And it gets updated whenever we get requests to it again, kind of like how dashboards work. So that's it for this tutorial. Hope you guys liked it. If you have any questions, feel free to drop them in the comment section and I'll try to answer them. Don't forget to hit like and subscribe, and thanks for watching. Bye.